So if you've been a MotoIQ fan for very long, you probably know that I'm a huge proponent of the Honda K motor. The K motor is one of my favorite engines because it has a huge amount of aftermarket support. The cylinder head flows like no other, and it can make a tremendous amount of horsepower in boosted or naturally aspirated applications. So let's get into what we do with K motors and talk about the insides. So for our build, we're going to start off talking about pistons. And for us, when it comes to the Honda K motor, it's usually going to be a JE piston. You might want to know why we like JE pistons for our K builds. Well, JE has a piston for about anything you can dream up, and it's a shelf piston. That means it's off the shelf. You don't have to wait for a custom piston, and if you ever have a problem, like it's a race motor, you need to rebuild the motor mid-season because something happened, having a shelf piston can be a lifesaver. It's the difference between getting a piston like overnight and having to wait 6 to 10 weeks to get one. Now, like a lot of piston makers, their shelf piston is like, you just kind of got to take what they have. But JE has so many different combinations of K-series shelf pistons that you really don't need to compromise anything. JE has bore diameters, for instance, from the stock 87 millimeters all the way up to 94 millimeters. Now, when you bore one of these, you really don't want to go past 87.5 because the liner's not enough to accommodate a bigger bore than that, but you can always go sleeves, and that's how you can get the really big bores. Compression ratio is also really important. The shelf pistons, you can get them in anything from 9.25 to 14.25. So anything from a good turbo motor to all the way to a top full-on naturally aspirated build can be accommodated with shelf pistons. The JE piston can also take any common combinations of stroke and rod length off the shelf too. So when you're starting off trying to decide what piston to run, I guess you have to figure out what your end use is going to be. Is this going to be a turbocharged motor? Is it going to be naturally aspirated? What kind of fuel are you going to run? Is it for a particular class of racing, and are there any rules and restrictions? I guess I can give you some rough guidelines. For a turbocharged motor, especially if you're going to be running pump fuel, it'd be a good idea to run the 9.25 compression ratio pistons. This is a fairly high compression ratio for a pump gas turbo motor, but the K has a nice flat included angle combustion chamber with good quench and good turbulence, so it's pretty detonation resistant. This will allow you to run a slightly higher compression ratio and have more snappy response and better running off boost. And with more compression, you get on the spool a little bit quicker. If you're going to be running like maybe ethanol or a really high octane race gas, you can get away with as much as 11-to-1 in the turbo motor, but probably wouldn't push it more than that. And when I'm talking about turbo, I'm talking about, it could be supercharged, or it could be you're running a lot of nitrous. Any kind of forced induction, you don't want to go too crazy in your compression ratio. So I would say if you're running ethanol or maybe Q20 or something like that, VP or C16, you can get away with as much as 11-to-1. For a naturally aspirated motor, if you're going to be running on the street with pump gas, you might want to run something like 12-to-1-ish. You don't want to really go any higher with pump gas, and with 91 octane, that's pushing it, and you're going to have to be really conservative with your tuning. But if you run 93 in other parts of the country, you can get away with 12-to-1. That's a pretty good compression ratio for like a pump gas naturally aspirated. And if you're going to be running all out naturally aspirated motor, and you're going to be running something like VP C12 or ethanol or something like that, sure, go for 14.25. Get as much compression ratio as you can. You'll get the best thermal efficiency, most power, widest power band. There's diminishing returns, like if you're going to be running on the street, don't get too greedy with compression ratio. I mean, keep it to 12-to-1. And just because the piston is rated some compression ratio, you can kind of tweak around that a little bit. You can mill the head some, deck the block some, run different thicknesses of head gasket, be a little creative with valve enshrouding, all to get the volume up there or down there to tweak your compression ratios. So you can do tweaking without being too detrimental for other things, plus or minus half a point of compression. That's pretty much how you choose the piston. And I guess when you're choosing your compression ratio, it's best to err on the side of being conservative. Just run a little bit less hard than you think you might want to, especially you grassroots people that are on the budget and you don't want to hurt stuff. So for your K motor, you have your standard bore, and there's limits to what you can do with your standard bore. From the factory, they say that 10 thousandths of an inch is about the max that you can do with an OEM piston, but we can say that we comfortably bore up to 20 thousandths. I mean, if you look here, the cylinder liner is really thin, and you don't want to get too much into that. If you wanted to go bigger than that, you can have your block machined out for sleeves. A lot of times we don't like doing that because if you take out the whole center part of your block, if sleeving isn't done correctly, you can lose some structural integrity, and you can have problems with head seal and things like that. I mean, basically, you'll be turning your engine into a case for freestanding cylinders. Now, if this is done correctly, a lot of horsepower can be contained like that, but generally for a motor that is going to be something like road raced or a lot of different heat cycles near the max, we like to keep the integrity of the block, but that doesn't mean you have to. So you can go pretty big in the bore, up to 90 millimeters with sleeves. The other thing we like to do is you take the minimum out of the bore as you can. Let's say there's a lot of wear or scratching in the cylinder wall, or if somebody set the motor out with water in it and it got corroded. If it doesn't clean up with a 20 thousandths overbore, and then it's either time to sleeve or get a new block. So now we can talk about our specific recipe to kind of build a K motor. Now this is a pretty reasonable, semi-low budget bottom end. This will see you through plenty of horsepower, and we can build one that can take even more horsepower. But something like this can probably withstand 500 horsepower easily, and it's pretty reasonable in price. Some of that is the K block is really stout. This is a K24 block. Now the bottom end has this whole bed plate. Traditionally, engines just had main bearing caps, so each main bearing had an individual cap, and it wasn't unitized, so that wasn't nearly as strong. The K motor has this bed plate, so all the main caps and the whole bottom of the engine are unitized in this one stiff, super strong structure. So this supports the crank really well. It won't flex even with a lot of power, and it is super stiff, and it helps fortify the stiffness of the block. That kind of helps distortion overall, can improve your life of things, and even improve things like your ring seal. So when we do the block, this block has a lot of our tricks done to it. First off, we do all our boring and honing with a Flexplate. A Flexplate is a steel plate that's machined like the cylinder head, and you can assemble it with all the bolts or studs and fully torque it down, just like the torque of a bolted-on head. Now, when you bolt on the head, most blocks distort quite a bit, and it can make the cylinder go out around by over a thousandth of an inch. So, a thousandth of an inch is quite a bit. That's more than 1/3 of your total piston and wall clearance. If you get that distortion, your piston rings aren't going to seal well. There'll be some scuffing on your piston. Just everything won't wear as good. So when you put the torque plate on and do all your machining, it's like machining with the head on. So when everything's torqued, your bores are going to be perfectly round. So that's good for power, friction reduction, and longer life. So once we bore it, this was a pretty crusty block, and our customer didn't like it. So what we did is we had it vapor honed. So vapor honing process is you get a special media, and you basically blast the block with it, and the media is blasted with water. So the water acts like a cushion and a lubricant, and it'll take off all the crustiness and leave like a luster. So, you know, if you had sandblasted it or bead blasted it, it would be like this dull gray color. It would be really porous. So if you touch the engine with greasy hands, you'd have fingerprints in, and they wouldn't come off, and it would basically look like crap. But when you vapor hone, you get this nice luster, and it looks like a brand new block that just came from Honda. I mean, you can probably see that in this front cover too. Now these things were really crusty. They had a lot of white corrosion and a lot of baked on burnt oil and stuff. But I mean, when you look at it, nice, shiny, brand new, hard finish that doesn't leave fingerprints, and dirt and oil and stuff will just wipe right off. It's a really cool process. After vapor honing, we did all of our machine work. Then we sent the block to get cryogenically treated, and the bores WPC treated. WPC, we talk about it a lot. It's like a Japanese micro shot peening, where they blast the rubbing surfaces with a superfine ceramic medium that's super round. Gives it a really smooth finish, and the blasting kind of refines the grain, changes the grain structure, so it's a hard, smooth finish that cracks don't propagate, and it's really wear resistant. So when you do the things like your bores, your bore can probably last twice as long without having to be rebored. It also reduces friction, and your rings breaking quicker. Basically, we do it on everything in the whole engine that rubs. Cryo treating is like an extension of the heat treating process. Basically, you take the engine down to the temperature of liquid nitrogen and hold it there for a certain time, and you cool it down and heat it up like very carefully so you don't distort the part. Basically, that completely stress relieves the block and parts, and it also in the bores kind of converts any kind of iron into a harder crystal structure. So if you're in the metallurgy, it's changing austenite into martensite. The aluminum, it's a little bit of an extension of artificial aging, so the aluminum gets a little harder and stronger. It's a nice process for any engine that you want to last long and be reliable. So we cryo-treated, WPC'd, vapor honed, and the last thing we did was we ultrasonically cleaned the block. When you machine the block, there's all kinds of shavings and cutting oil and residue that can get into bad places where you don't want it to be. Same thing with vapor honing. That uses a really hard ceramic media that can get into places and you don't want it coming out. And WPC. Any of those things are abrasive, and they can really damage the engine if they come out in use. So when we've done all these treatments, our final step is to ultrasonically clean the block. Now we go to this aerospace place that specializes in ultrasonic cleaning, and what they do is immerse this thing in the tank, bombard it with ultrasonic waves. It causes agitation and literally knocks all the particles out of the whole block. They also pump the cleaning fluid through all the passages while undergoing this ultrasonic agitation. It gets the engine surgically clean. So if the engine's been subjected to a lot of different media, we always do the ultrasonic cleaning before we reassemble it. So what we have here is our basic bottom end assembly. This thing can take like 500 horsepower all day. And if you wanted to go full ham, I mean, we can build you one that could take as much horsepower as you dream up, because there's all kinds of levels of stuff. Like there's billet cranks, billet blocks, you name it. But for a reasonable budget, what we have here is fine, and it'll be totally reliable, and it'll pretty much kick ass. We're going to start off with a stock K24 crank. And this is a nice forged crank. It's fully counterweighted, and it's nitrided from the factory. All we really did is balanced it. We micro-polished the journals, cryogenically treated it, and WPC treated the journals. This kind of crank can handle a lot of power. It can handle probably like 8,600 RPM totally reliably. If you want to rev consistently higher than that, we might want to put a tricker crank, but there isn't too many situations where the stock crank can't handle it. I mean, I really like this stock crank. It's a good piece, and it doesn't take that much to make it really good. For connecting rods, we use the K1 rod. Now, this is a really good rod for the money. It has a really good price. That's the most important thing. The rod is machined out of 4340 like a forging. And what's interesting about this particular forging is it's a near net shape forging. So what that means is when this thing's forged, they get a piece of metal, put it in the die, and coham it with a ton of force, and it comes out, the big end and little end comes out. Now, a lot of rods are cut from billet, and like you have your grain going, usually this way, which is pretty good, but then your grain flow around your cap is still like that. When you get this net shape forging, the grain flows down the beam, but it also goes around the big end of the rod. And that actually gives it a lot of strength and toughness without, adding weight and all that. So it's a near net shape forging that has the final machining. There's some cool features. The oiling holes there's one here and one here. They're on the bottom part of the rod. A lot of rods have a big oiling hole at the top. The reason why they're having the oiling holes on the sides is important, or why it could be better, is this is like a part of the rod on the top that's pretty highly stressed, because the pin wants to yank out of the top of the small end when it's accelerating. And when you remove material here, that creates a weak spot. So there's a lot more material around the base of the small end. So having two small holes, it can be better than having one big one at the top. The rod bolts, this is really important. This is the most highly stressed part of the rod. They're ARP 2000 bolts, which is kind of the industry standard for a good rod bolt. They're 200,000 PSI strength, which is really good. It's good enough for quite a bit of horsepower. There's tricker rod bolts you can get if you want to go huge horsepower, but ARP 2000s are way better than stock, and they're good for 90% of the time. Another nice thing is after machining, this rod is solution heat treated, so that brings it up to like a higher level of strength. Like what it'll do is all the metal in here gets to solid solution temperature, and what that is when it's actually the solid shape, but scientifically I guess you could say it's a liquid, so all the alloying elements are all freely circulating around in the rod. Now when you're at solid solution temperature, all the alloying elements are going to arrange themselves evenly throughout the rod, and you can actually fix the crystal matrix of the metal by quenching it at the right temperature and time. So you can actually get a higher tensile strength and better fatigue properties by quenching it and controlling the crystal structure of the metal to what you desire. The final thing is that they do a severe shot peening. They use a small shot and a big shot. Small shot gets into all the little tight radiuses, and the big shot imparts a lot of compressive force on the surface of the part. So the shot peening creates a skin that has a lot of compressive stress, and it also causes a lot of grain refinement on the surface. So it makes the grains fine and tight, and it's a skin over the whole part. Now, when you have compressive stress and finely grained skin, it's really hard for a crack to get started and propagate throughout the rod. So what that means is the amount of cycles that the rod could take before it breaks is basically doubled with the proper shot peening. I guess some of the normal things has a silicon bronze small end bushing, which is kind of typical for a high quality rod. But most of all, you get all this at a great price. To hold the bomb end together, we use ARP 2000 studs. The studs are better than the factory Honda bolts that tend to get stretched out after one cycle of tightening. The ARP studs have a strength of 200,000 psi, which is way more than stock, and basically holds the bomb end together a lot better. So the studs have like nuts with the equivalent strength, and they also have ground hardened washers. So these are super flat washers, really hard, help you get a consistent torque reading when you're tightening them. For bearings, we use the King XP bearing. We've had really good luck with the XP. Some of the cool things about it is it's a tri-metal bearing. So the main layer, the overlay is lead, but it has a high tin content in the alloy. The tin makes the lead a lot harder and increases load bearing capacity. So the tin alone gives like about a 20% advantage over your typical bearing material. The other thing about the King bearing that's cool is it has a black top coat. Now, coated bearings are not a new thing. They're usually there to provide some lubricity. If any part of the crank touches down during the operation, it prevents the crank from getting into the softer lead overlay. The big thing about the King coating is that it has a 5% content of copper nanoparticles. Now these copper nanoparticles make it so the coating actually increases the load bearing capacity. Usually coatings don't do anything for that. So the coating gives you about another 12% more load bearing capacity. So that's a King innovation that works really well. We've had incredible luck with King bearings. Like we've run racing motors for a whole season, take them apart, bearings hardly look worn. We could probably just like put them right back in if we wanted to. Usually when you're doing actual racing, like road racing or drifting, where you're really on the throttle for long periods of time, there's usually significant wear after a teardown interval. But King bearings seem to hang probably better than other bearings that we've used in the past. So of course, like we talked before, we're going to be using JE pistons with this engine. This particular engine is going to be a hot, naturally aspirated street motor. So the compression ratio we chose is 12:1. Of course, it's a shelf piston, and there's no compromises here. This is just as trick as a custom piston. One of the things you might notice first is an asymmetrical skirt. A lot of race pistons have what you call a slipper skirt, so that would be a skirt like this size. It's a really small, minimalized skirt that's cut down to the minimum. This gives the lightest weight, least amount of friction, but there's a lot of point loading and a lot of wear. So the JE piston on the thrust side of the piston that sees the most load, you notice it's way wider. So it's almost as wide as a full skirt piston. So this kind of spreads out the load, reduces wear, reduces rock in the bore, which can make piston slap noises. Basically, you get the best of both worlds. You get the support of a full skirt piston on the thrust side, and you get the low friction and lightweight of a slipper skirt on the non-thrust side that's not as loaded. This forging that's used for the K motor was designed especially for the K motor, so its net shape is really just about perfect. So you don't need a bunch of after milling. I mean, there's some minor underground milling to reduce some weight, but it's not like you're starting off with this big buildy thing that you have to carve the heck out of it. basically a near net shape forging with minimum underground machining that ends up being more inexpensive. It's a better, when you have a near net shape forging, you have better grain orientation and everything. It's kind of a win-win. A little extra is the JE piston comes with skirt coating, anti-friction coating that you normally have to send your piston out to. If you see these little pads here, that's where your micrometer goes to measure your bore so you can set your piston to wall clearance. That's a good plus that, it's a no cost extra. The piston pin is your standard steel pin. We don't like to get too fancy. A nice straight wall pin usually doesn't flex and doesn't give you trouble. A lot of times in the past, a tapered wall tool steel pin was the hot tip, but we've kind of found that as motors output has gone up more and more, a tapered wall pin wants to flex under load, and that tends to catch on the small end bushing and spin it out of the rod. And that is not good and usually causes catastrophic failure. Another feature is there's a gas accumulator groove between the number 1 and number 2 compression rings. The accumulator groove helps get gas pressure underneath the second ring under all times and improves your ring seal without increasing your tension. The accumulator groove is especially handy at high RPM. A lot of high-end racing pistons have this feature, and it's something that's come into play probably over the last 10 years. Overall, I mean, this is a really good piston. It has a lot of features of a custom piston. It doesn't give up anything to a custom piston, and best of all, it's off the shelf. So piston rings are an important part of the piston package. And a lot of people don't think much about them, but the rings that JE supplies with their shelf pistons are actually really high tech. They're a low friction design. That means they're really thin, and also their thickness here is really thin. In the old days, these kind of rings were race only, and they used to not last very long, and there'd be a lot of leak down, they'd burn oil, and it was a really tweaky thing to try to do, and you would do it with gas porting, get pressure behind it, but really low friction at other times. But ring technology has improved so much that they're actually practical for long-term use. The metal that's used in rings is a lot more sophisticated. You get a steel alloy, better alloys of iron too in the second ring, steel first ring, better metals in the scraper. The number 1 ring is a steel ring. It has a barrel shape and it's nitrided. Nitriding, they cook these things in a atmosphere with cyanide and stuff, and at high temperatures, and then that causes the outer surfaces of the ring to have a lot of iron nitride form, which is a really hard, almost ceramic type crystalline structure that actually penetrates into the ring. Like old school rings, maybe they're chrome plated, but nitriding is actually harder, more durable, and more slippery. So with a nitrided ring, it's small, has this slippery outside, and really hard, lasts a long time. The number 2 ring is like a ductile iron. What's trick about this is it has what's called a Napier profile. A Napier profile has a little hook in there. The hook actually kind of helps trap gas to put some more radial pressure into the cylinder wall for better sealing. It also has a really thin edge that wears into and conforms to the cylinder wall really quickly, gives you fast break-in. Most JE pistons have a Napier second ring, and even though these are really thin, really low tension, really low friction rings, we've never had a durability or a oil burning problem. The oil rings man, it's really thin. Like the separator's thin, and the rails are like paper thin. You know, with Jay's technology, this super thin, low tension oil ring does its job. Like I said, we never had a problem with excess oil consumption or lack of life. Some of the tricks we do when we assemble an engine, the entire rotating assembly is balanced. We measure every single journal on the crank in several places. That way we know the true journal diameter, and if it has taper wear or if it's out of round or anything. Then we assemble the bottom end, bring it up to torque, and that way we measure the bearing bores for the main, and that way we know your true bearing clearance. We can adjust it a little bit by massaging the crank or massaging the different bearing shells that we use. So that way we get nice, consistent clearances for your bearings. Now most shops just throw it stiff together, but you know, we found that a lot of times you get tight spots. There's a lot of friction. That means there's a lot of wear because something is not straight. Now, if we have like problems with that, we align bore everything and get everything nice and straight and perfect. Controlling the main bearing clearances are important, especially with modern aluminum block engines. The thing is, the aluminum grows, so the clearance can grow with temperature. And if you don't keep those bearing clearances like really nice and tight, you can start losing oil pressure. And we've seen engines that other people build, and they have almost zero oil pressure when they're idling and hot, but you won't see that with our motors. We take a lot of time to get the clearance right. We also machine the decks to make sure they're flat. We take out the minimum possible material, and we also use a really fine finish, so if you have an MLS gasket, it'll seal no problem. When we machine our bores, we just don't tell the machine shop, oh yeah, take it out 20 thou over. A lot of engine builders do that. What we do is we measure each individual piston and we number it. Then we number our bores and we tell the machinist like how big we want each individual bore. So each piston is fitted to its individual bore. That way you get a lot of consistency. That's all helping life. Friction controls piston slap noise, controls oil consumption. It's all good. Another trick we do is we always get oversized piston rings, and we actually blueprint each ring so the end gaps are perfectly the same for every cylinder. We have a little machine that we can grind the ring gaps and make them perfect, but each ring set is hand fitted for each cylinder. So if you like this video and you want to see like what we did with the top end and things like that, for the top end, generally we like working with Drag Cartel. We like their cam grinds, we like their head work. So a lot of our top ends feature a Drag Cartel head. This engine is pretty identical to Project RSX on MotoIQ. So if you go to MotoIQ.com, look at Project RSX. We also had a build for a Ariel Atom with a very similar motor. Both of these motors produce more than 300 wheel horsepower with 91 octane supercraft California gas. They're pretty conservatively tuned, and they're both still alive. So if you want to know the part numbers of what we used here, check out the description of this video. They're going to be in there. We'd like to thank J Pistons and K1 Rods along with ARP for helping sponsor some of this, and hopefully you enjoy this video. So if you want to see more, go to MotoIQ.com, read all of our hundreds and hundreds of articles that are highly technical there. Be sure to mash that subscribe button, subscribe to this channel, and also visit us on Instagram and Facebook. So until next time, we'll see you later. Hopefully we'll be getting into more engine tech.